visible and left over visible.
Yeah. Come on, open this. Let's pull it. No. Okay. Live. And call. You end it. All right. Good day and welcome to AFD'S Academy. I am Arthur Francis Deban. Sorry, the live session was a little bit delayed in the course of the changes in events. All right, today we're going to be dealing with redox reactions, and redox calculations. So, when we talk about redox reactions, there are two things which we must put into cognizance, which are probably the oxidation and reduction. These two reactions takes place simultaneously in a redox reactions. So by virtue of that, our knowledge of what oxidation is and reduction is becomes pertinent, because if we're unable to differentiate and identify in a given reaction what oxidation is or reduction is, our idea of balancing any redox reaction becomes almost impossible. So what is oxidation by the theoretical framework of our explanations? We say oxidation is the gain of oxygen, the loss of hydrogen, and the increase of oxidation number in terms of electron transfer. While reduction is the loss of oxygen, the gain of hydrogen, and the decrease in oxidation number in terms of what? Electron transfer. So when the oxidation number of a system increases, we say oxidation. When in balancing of reaction, the oxidation number at the end of the day increases, we say oxidation takes place. When it reduces, we say reduction takes place. And when there is what? Addition of oxygen in the process, we say what? Oxidation takes place. There is loss of hydrogen in the process, we still say oxidation takes place. Remember that. That's oxidation by definition. So I'll give us a few equations so that we'll be able to identify oxidation and reduction in those equations. So let's take this out. So if we are to define oxidation and reduction, again, we have to look at this equation and see how they are being applied. We say oxidation is the addition of oxygen, the loss of hydrogen, and the increase in oxidation number. While reduction is the loss of oxygen, the addition of hydrogen, and what? It reduces in oxidation number. So if you look at copper sulfate plus zinc, we will say, look at copper sulfate contains oxygen. By terms of oxidation number, we say copper here loses what? It loses what? Its oxygen. So copper sulfate has been reduced to copper because reduction is the loss of oxygen. Now, this reduction takes place, copper loses its oxygen to form what? Copper, because we say reduction is the what? Loss of oxygen of a substance. Why? Oxidation is the addition of oxygen to a substance. So now let's look at zinc. Zinc now gain oxygen in the cause. We have zinc sulfate. So there is addition of oxygen to what? This zinc. We say zinc has been oxidized. This zinc has been oxidized in the product. Look at the reactant. We have copper sulfate. The copper is being reduced to copper by what? Losing oxygen, because oxidation is the loss of oxygen, the addition of hydrogen, and the increase of oxidation number. When we define it in terms of electron transfer, we say is what? The addition of what? Increase in oxidation number to that end. So by that definition, oxidation is the loss of oxygen. Oxidation is the addition of oxygen. So zinc has been oxidized. It was zinc, it becomes zinc sulfate because oxygen has been added. Now, copper sulfate now loses oxygen to form copper, and we say reduction is what? The loss of oxygen. So by virtue of that, in this equation 1, we say copper has been reduced from copper sulfate to copper, and zinc has been oxidized from zinc to zinc sulfate. So that is settled. Equation number 2, lead oxide plus carbon. So the loss of oxygen is what? Reduction. So lead oxide becomes lead. It has lost its oxygen. So lead is being reduced. From year to year, it has been reduced. And if you check the oxidation number of lead here, it's -2. And here, you calculate days too. So you say that lead oxide has been what? Reduced by the loss of what? Oxygen. But carbon has been oxidized by the addition of what? Oxygen. Oxygen has been added. So we say carbon here is what? Oxidized. From year to year, it is oxidized, while lead from year to year, it is being reduced. Copper oxide loses its oxygen, so reduction takes place here. Why? Hydrogen here now gets what? Addition of what? Oxygen, oxidized. We'll come back here, manganese, 4 oxide and hydrochloric acid. Look at manganese, we now have manganese chloride. Now, manganese lost oxygen to be what? Reduced. Look at the hydrogen. Hydrogen now, in this sense, when we compare it with this, or let's take to the chlorine, the loss of hydrogen, remember oxidation again. We say oxidation is the addition of oxygen, the loss of hydrogen. We say that hydrochloric acid has been reduced to chlorine by the loss of this hydrogen. So by definition, what do we say? Oxidation number is the addition of oxygen. Addition of oxygen, removal of hydrogen, and increase in oxidation number. Now, addition of oxygen, removal of hydrogen. See, this guy has removed hydrogen, so it is what? Removal of hydrogen, addition of oxygen, that's oxidation. Addition of oxygen, yes. Removal of hydrogen. So in that case, it has removed its hydrogen to what? Chlorine. So we say it is oxidized, because by that definition, that is what? Oxidation. So it is easy if you look at it carefully. But if you don't, it looks as if it is complicated, okay? So let's define it for the last time before I move on from this area to some other section. Oxidation and reduction takes place simultaneously in a redox what? Reaction. They happen the same time. And we say oxidation, by its own definition, is the what? Addition of oxygen to a substance, removal of hydrogen, and the increase in what? Oxidation number, and so on. So we are going to move on from here to another section. So redox reactions, by definition, we have 2 types: the simple and the complex. The simple redox reaction and the complex what? Redox reaction. But I'm going to solve maybe one or two questions in the simple. Our business today is that of the complex. But in all things, before we begin to understand how we can balance our redox reactions, our knowledge of oxidation number becomes what pertinent. We must know or remember how to calculate our oxidation number, because in terms of calculating or balancing of redox reaction, we make use of oxidation number method. So our knowledge of how to balance or calculate the oxidation number becomes very, very important. So I'm going to take a couple of questions in terms of oxidation number, how to calculate the oxidation number of substances. Then when we know that, we can now proceed to start balancing our redox in terms of the simple and the complex. So let's start with a very common one, which we should all know. So we say the oxidation number of H2SO4. Now, for us to begin, our knowledge of the valency becomes important. How do you know the valency of hydrogen or oxygen, or their oxidation number alongside? So we say that the oxidation number of all group 1 element is +1. All group 2 is +2. All group 3 is +3. By virtue of their valency, the number of electrons in their outermost shell. Let's take potassium. Okay, let's take sodium, for example, has atomic number 11. By my electronic configuration, this is 281, which is 11. Now, the number of electrons in its outermost shell is 1. It means that sodium belongs to group 1 and its oxidation number is 1. If I take magnesium, which is 12, means I will be having 282. Now, the number of electrons in its outermost shell is 2, which means it has a valency of 2 and the oxidation number of 2. So also potassium is 2881, which is 19. That means the number of electrons in the outermost shell is 1, and so the oxidation number of potassium is 1. So in terms of the rules, that is how it goes. And we say the oxidation number of oxygen is -2 in all substances except peroxide. And we also say the oxidation number of all the elements in the compound is equal to 0. And also we say the oxidation number of any charged element or ion is equal to the charge. For example, aluminium 3+, the oxidation number of aluminium here is +3. SO4 2-, the oxidation number of sulfur in this place now is -2. That's how we begin before we can proceed further. So these are the basic rules which by now you are supposed to have known. But for the sake of clarity, I just have to touch on a little bit before I start solving questions on oxidation number, so we're not going to be confused. So let's go back. So we have our H2SO4. We're looking for the oxidation number of sulfur in this compound. Remember the rules. The oxidation number of all the elements in the compound is equal to 0, so I equate this to 0. Hydrogen is in group 1, so its valency is +1 times 2, which is attached to it, put in the bracket, plus sulfur is what I'm looking for. So I'm going to still use sulfur. Most literatures will use X, but I'm going to use sulfur so that we know what we're looking for. So this is plus sulfur. Then plus oxygen, we say it is -2. The oxidation number of oxygen is -2, except in peroxide. So -2 times 4 is equal to 0. 1 times 2 is 2, plus sulfur, plus times minus is minus, 2 times 4 is 8. And this all is equal to 0. So sulfur is equal to, make this the subject, -8 crosses over the quality sign, become +8. +2 crosses over the quality sign, become -2. Now sulfur is equal to +6. And in oxidation number, we always put the sign. If it is plus, put it. If it is minus, put it. If you do not put it, you tend to lose some marks. So that's very important. So by this, we've been able to calculate the oxidation number of sulfur in this compound. And that is why the name of this compound is called tetraoxosulfate 6. Tetraoxosulfate 6 acid. So don't forget that. Let's take another example. Example 2 is HNO3. We are calculating the oxidation number of nitrogen in this compound. So this already is equal to 0. Hydrogen is +1 plus nitrogen plus -2 for oxygen times 3. All this is equal to 0. So this is 1 plus nitrogen plus times minus is minus, 2 times 3 is 6, equals to 0. So making nitrogen the subject, this become -6 crosses over become +6, 1 crosses over become -1, and nitrogen is equal to +5. So the name of the compound is known as triazonitrate 5 acid, because the oxidation number of nitrogen in this compound is +5. Now let's take another one, Na2CO3. We're looking for the oxidation number of carbon, so we're looking for carbon. First thing is we equate everything to 0. Sodium is +1, there's 2 there, 2 times 2. Plus carbon, which I'm looking for, plus oxygen, which is -2 times 3. This is equal to 0. So this is 2 plus carbon, plus times minus is minus, 2 times 3 is 6. All this is equal to 0. So making carbon the subject, this is equal to -6 crosses over become +6. And +2 crosses over become -2. And carbon is equal to +4. So it is called triazocarbonate what? 4. Because the oxidation number of carbon in this compound is +4. This is straightforward. You need to know the group and the period which all your element belongs to. By virtue of that, it becomes easy for you to navigate. But if you don't, it becomes difficult. I forgot, in the rules, all halogens have a valency of -1, while oxygen is what? -2. Let's take another example. So now we say we have another one, SO3 2-. So this is -2. Remember I said that the oxidation number of this element is equal to the power of the charge. All right, the power of the charge. So by virtue of that, I would be having SO3 is equal to what? -2. Okay, SO3 is equal to -2. That's what I'm going to have because it's equal to the power of the charge. So by virtue of that, I will have to proceed. All right, I'm looking for that of sulfur. So sulfur in bracket. I'm looking for the oxidation number of sulfur. So whatever is in bracket is what you're looking for. So this becomes sulfur plus oxygen is -2 times 3. This is equal to -2. So sulfur plus times minus is -2 times 3 is 6. This is equal to -2. So sulfur, you know how to deal with them. That is going to be nice. So let's take another one. Permit me if I have to take this out. Okay, I have ClO3-. Okay, this means that Cl, this is small l, O3 is equal to -1. So my chlorine, which is, I'm looking for chlorine here, plus oxygen is -2 times 3, all equals to -1. So chlorine here, plus times minus is -2 times 3 is 6, all equals to -1. So Cl is equal to -1 plus 6. And my Cl in this sense become +5. Okay, let's move on. Let's take one more, probably the last one, on oxidation number, so we can go into the balancing quickly. Now we have this, which is KMNO4. We are so conversant with this, we'll be using it too many a time. By now, you will know that the oxidation number of this compound is +7 without even starting the calculation. So, but then we still have to find out how do we get the 7. So this is equals to 0. Now potassium is +1 plus manganese plus oxygen is -2 times 4. This is equals to 0. Right? So now this is +1 plus manganese, plus times minus is minus, 2 times 4 is 8. All of base is equals to 0. So my Mn is equals to -8 crosses over, become +8, +1 crosses over, become -1, and my Mn is equals to +7. So this is potassium tetraoxomanganate 7. So we'll be dealing with this quite a time, so we should know that. So now, having undergone the principles of balancing or calculating of oxidation numbers, we are going to move into balancing of redox reactions fully. And remember I said in the course of us balancing our redox reaction, we have two methods. We have the simple redox reactions and the complex redox reactions. Our job today is to deal with the complex, but for the sake of clarity, I just have to touch a little of the simple redox so that you see the nature in which they appear before we can delve directly into that of the complex. So let's see a practical example. Okay, we have iron 2 plus chlorine molecule gives us iron 3 plus chlorine ion. So this is our equation. We want to use the simple redox principles. First of all, we have to identify oxidation and reduction. So I will say oxidation and reduction. Now, we see oxidation in terms of electron transfer is the increase in oxidation number. So we have iron 2 to iron 3. There is what? An increase in oxidation number. So I have iron 2 plus to iron 3 plus. In reduction, we say is the decrease in oxidation number. Here, the oxidation number is 0. And here it's -1, so it's moving towards the negative from 0 to -1, so it's decreased. So in reduction, we say we have Cl2 to Cl minus. All right. Remember, we say electron. Now, in this case, if you check the difference from 2 plus to 3 plus is 1, means it has lost what? 1 electron. So by that standard, I will now have, since we say it's loss of electron, iron 2 plus loss minus 1 electron will give me, yeah, this is minus, take note, let it not be too long, gives me iron 3 plus. And this side, because of these two, we say that it is the gain of electron. Look at this one is loss of electron. So here I will have chlorine 2 plus electron. It gains electron, gives us Cl minus. But by virtue of these two, which means we have to reciprocate it in terms of the ion, we are having our 2 here and our 2 here to balance it. So now there we are. This we have to place it as simultaneous equations, having our equation 1 and our equation 2. So let's take this as equation 1 and bring this down. Cl2 plus 2E minus is equals to 2Cl minus. So this is equation 2. By simultaneous equation, it says you multiply equation 1 by 2 and equation 2 by 1. Multiply equation 1 by 2 here becomes 2Fe2 plus minus 2E negative gives us 2Fe3 plus. And when we multiply this by 1, we still have the same thing, which is Cl2 plus 2E negative gives us 2Cl minus. Now, we take the reactant and our product. So by taking our reactant, I feel like, let me take this out, please. You've noticed, you've taken that already. Let me bring it up. I will now have this other side, I have 2Fe2 plus chlorine molecule. This side, let's leave the charges. Gives us 2Fe3 plus 2Cl negative. Now let's balance, let's check the charges to know whether the equation is balanced. This is the end of the reaction, but we have to check our charges to know if they are balanced. If it is not balanced, then we have to check what could be wrong. In charges, 2 times 2 here, you have plus 4. This is 0. This is 2 times 3 is plus 6, sorry. And this is plus 2 times minus, this is minus 2. Now, 6 minus 2 is 4. And this side is 4. The left hand side is 4, the right hand side is 4. So our equation is balanced. So by simple redox reactions, we've been able to illustrate how to balance it. It's different from complex. Our business, like I said, is complex, but that's where we're going. But I just need to show us that in case of necessity, you may bump on certain questions that have to deal with simple. And you'll be like, how do I know complex? And I do not know simple. So let's take a couple of the simples before going to the complex. So this is it. That equation is balanced. We're going to take another one at least before anything else. So permit me to clean this out now. Okay, we have copper 2 plus zinc gives zinc 2 plus copper. Okay, like we did, we check oxidation. Oxidation is the increase in oxidation number. So if you see here is plus 2, here is 0, it increases toward 2. So that is oxidation. So by virtue of that, I will now have Zn tends to Zn2 plus. Reduction now. Let me not use this arrow. Let's call this a reduction. Is the decrease in oxidation number from plus 2 to 0. So I have copper 2 plus tends to Cu. Copper. So remember we said that oxidation is the loss of electron. So Zn minus, let me put Z first, Zn2 plus. But remember, I have not put the charge. Let me put the charge first. Minus what? Electron. Minus electron. But now, how many electrons? From 0 to 2, there is 2. So it means there are 2 electrons displayed. This gives us our Zn2 plus. Then this is equal to, in the reduction, we say is the addition. Is the addition, yes, of electrons. So we have 2 plus how many electrons? From 0 to 2, that's 2, plus 2E negative. That's the charge. That gives us our copper. So by virtue of this, we equate equation 1 and 2. So this is our 1, that is our 2. So I have Zn minus 2E negative give us Zn2 plus. Let me show you something. Many literatures will write this equation as this. Zn give us, in terms of oxidation, Zn2 plus 2E electron. It's the same thing. Because if you cross this across the quality sign, this is what you get. But before this sign, it is giving you your minus. So I prefer using this, but these two things are the same. In case you come across a lecturer or anybody who teaches you anything similar to this, who tends to be using it this other way, do not think that, why is your own different? They are the same thing. But I'm using this principle in terms of the definitions of oxidation. Oxidation is loss of electron. So we see the loss. Gain of electron, we see the gain. So that's how I place them side by side. And many other literature share with me the same philosophy. So I choose the one I'm using right now. So this is our equation 1. And this is plus 2E negative give us copper. And this is our equation 2. That rule that says we should multiply equation 1 and 2, equation 1 with 2 and 2 with 1. You realize that, okay, if we multiply this with 2, okay, let's just see what happens. You see if it's going to change. And equation 2 with 1, is there going to be any difference? 2 with 1, this with 2. If I look at it, let me see, 2 here and 2, this gives me 4. Okay, in the other side, since the charges here are the same, we cannot apply that rule. In terms of the charges, since they are the same, in the other case, we were having one is minus E negative and the other one is minus 2 positive. So in that sense, they were not equal, we multiply. But in this sense, we check the charges, we have 2E minus, we do not apply the rule, so we finalize from here. Take note. Since you check the charges here are the same, you stop there. But if this were to be 3, so you have to proceed by multiplying simultaneously. So I will take the reactant, which is Zn plus copper 2 plus, gives us equation 1. Okay, this is it. Gives us Zn2 plus copper solid. So we have to check our equation to see how balanced it is. This is 0. This is 2. 1 times 2 is 2. So I have plus 2 here. I have plus 2 here, and this is 0. So it's balanced. So we say the left-hand side is equivalent to the right-hand side in terms of what? The charges, which is 2, 2. So this is the second example in terms of what? The simple redox reactions. We're going to take a complex redox reaction. Let's see how that one looks. What's the difference between that of complex and this of simple? Obviously, I believe we're going to see a lot of differences, but let's begin. Let me take this out and bring up one complex. All right. Let me hold it in hand. So I have my MnO4 minus plus SN2 plus gives us Mn2 plus iron 3 plus. So this is that of a complex reaction. Let us begin. In that of complex, there are many things we're going to do. We state out the oxidation numbers, that's number 1. We check the difference that exists between them and cross multiply, that's number 2. We balance oxygen and we balance hydrogen. If you go through your work, which I've taught earlier on, you see the rules stated therein, but I don't have to be stating the rules here again, but let's just proceed. So this one is plus 7, this is 2, this is 2, and this is 3. So the difference from 7 to 2, which is reduction, the difference between the two is 5 in terms of manganese. And the difference between, I don't think these two things don't look the same. I think I've made a mistake. Let me check very well. Okay, SN2 plus. Oh, that one is SN4 plus. SN4 plus. So that was my mistake. So now let's look at it. Here is, like I said, here is 7. Here is 2. Here is 2, and here is 4. Okay, the difference between this and this is 5, and the difference between this and this is 2. So I cross multiply. Wherever, remember manganese contains 5, but wherever I see this guy, I put 5 before it. Yes, and the difference between these two is 2. Wherever I see manganese, I put 2 before it. So let us check it out. So this is my manganese. I'm going to put 2 before it from the difference between those two. So I have 2 MnO4 minus plus 5 SN2 plus give us 2 Mn2 plus 5 SN4 plus. That's 1. 2, a balanced oxygen. By the left, right hand side, oxygen here is 8. And here, I don't have anything. So I have to introduce a molecule of water that will contain oxygen. So I have 2 MnO4 minus plus 5 SN2 plus gives me 2 Mn2 plus 5 SN4 plus oxygen here is 8. So I'm adding 8 molecules of water, which give me oxygen 8. So now, if oxygen has been added here is 8, I have to balance hydrogen this other side. So I will have 2 MnO4 minus plus 5 SN2 plus hydrogen is 16 plus 16 hydrogen ion gives me 2 Mn2 plus 5 SN4 plus 8 H2O. Now we have to check if our equation is balanced. 2 times minus 1 is minus 2 plus 5 times 2 here is 10 plus 16 plus 16. This is 26 minus 2, which is 24. 2 times 2 here is 4 plus 5 times 4 here is 20. 4 plus 20 is 24. So I will say the equation is balanced because of the charges are the same. So this is how complex it is. It is a little complex too. So we're going to take more questions to see what we can do, and so that we become conversant with it. First of all, calculate the oxidation number. You know by now how to calculate the oxidation numbers. Well, in case you say you don't know, maybe I should, in next time, calculate the oxidation number. Yeah, I'll show you how it is plus 7. Yeah, I think I have some more questions to that end. So let's see. In our next question, maybe I will calculate that, but I'll clean it up before I continue. So let me take this out. So we are going to take our next question, which is manganese O4 minus plus iron 2 plus gives us manganese 2 plus iron 3 plus. So let's see. Now, we said earlier on that the oxidation number of manganese here is 7 plus 7. Let me just show us how we got that before we can move on. So I have my manganese O4 is equal to minus 1 according to the rule, equivalent equals to the charge. So this is manganese which I'm looking for, plus oxygen is minus 2 times 4 or equals to minus 1. So I have my manganese plus times minus is minus 2 times 4 is 8 equals to minus 1. And manganese is equal to minus 1, minus 8 crosses over become plus 8. And my manganese is equal to plus 7. So that's how it is 7. So I know that here is 7, here is 2 by the charge, here is 2 by the charge, here is 3 by the charge. We can see that clearly. So if this is 7, let me take this out so that we can go back. So if that is 7 actually, so 7 minus 2 is 5. This is MnO4 minus 1 of it. So plus 5 iron 2 plus give us 1 Mn2 plus 5 iron 3 plus. The next thing is addition of what? Balancing oxygen by the right side of the equation. And remember, by we adding oxygen is for us to add what? Water that contains the number of moles of oxygen here. So I have my MnO4 minus plus 5 iron 2 plus gives us Mn2 plus 5 iron 3 plus oxygen. We have 4 moles of oxygen here. So I will have 4 moles of water, because by 4 moles of water, I will have 4 oxygen. Now I have 8 hydrogen here. I have to balance hydrogen this side 8. So I will come over here. I have MnO4 minus plus 5 iron 2 plus 8 hydrogen ion give us manganese 2 plus 5 iron 3 plus 4 H2O. Now let's check our equation. This is minus 1. This is 5 times 2, 10 plus 8. 18 minus 1 is 17 equals to, this is 2. 5 times 3, 15. 2 plus 15 is 17. We say the equation is balanced, 17. So, if you ask me, I'll tell you, it's straightforward and it's simple. If you follow the rules, you get to the end of it. So let's take more questions. Okay, I've taken 2 now. Let's take one more, some more, not one more. Okay, our third question is this. Still MnO4 minus plus chlorine minus give us Mn2 plus chlorine molecule. So here is 7, here is 2, 5. So I put 5 here, and here the difference is 1, because this lot is 0 and this is minus 1. So the difference there is 1. So the same thing happened here. So I have my MnO4 minus plus 5Cl minus give us Mn2 plus 5Cl2. Okay. Yeah, let's move. Balancing of oxygen. Here I have 4 moles of oxygen, so I'm going to add 4 moles of water there. So I have MnO4 minus plus 5Cl minus give us Mn2 plus 5Cl2 plus 4 moles of water. Okay, so let's proceed. 4 moles of water, I'm going to add 8 hydrogen ion this side. So I have MnO4 minus plus 5Cl minus plus 8 hydrogen ion gives us Mn2 plus 5Cl2 plus 4 moles of water. Let's check. Minus 1, 5 minus 5 plus 8. 8 minus 6, that's 2. This is 2, 0, 0. Okay, 2. So it's 2 is to 2. It's balanced. So we don't need much stress on this. So that is how we move. That's how we go. You should just get yourself acquainted to it. So let's take maybe 1 or 2 more, so that you have a lot of questions you can do with. You can look into in case of necessity, in case you are confused. You can always look into them and solve as many as possible. So let's take this MnO4 minus plus H2X Mn2 plus sulfur. Okay. Here is plus 7, we know, but here is what? Let's calculate here. H2S is equal to 0. This is 1 times 2 plus sulfur equals to 0. So sulfur plus 2. So this is 2 plus sulfur is equals to 0. So now sulfur is equals to, take this as minus 2. So here is 2 minus 2, and here is 0. Now, remember, from here to here is oxidation. From here to here is reduction. But let us ignore. We ignore the signs, which is 2 here, minus 2, and this is 5. This is 7, this is 2. So 7 minus 2 is 5. 0 minus 2 is minus 2, so ignore the sign, we call it 2. So let's proceed. So in this side is 2, in this side is 5. So wherever I see this, I put 2, I see this MnO4 minus plus 5 H2X give us 2 Mn2 plus 5 sulfur. Or balance oxygen the other way. We have 8 moles of oxygen here. So I have 2 MnO4 minus plus 5 H2S give us 2 Mn2 plus 5 sulfur plus 8 moles of water. Okay, remember we have oxygen 8, 2 times 4, 8. So oxygen must have to be 8 here, 8 moles of this. So that's for our oxygen. So we're going to balance hydrogen this other side with 16 hydrogen ions. So 2 MnO4 minus plus 5 H2S plus 16 hydrogen ion give us 2 Mn2 plus 5 sulfur plus 8 H2O. Let's see if by any way or means that is balanced. So we have 4 here. Good. We have 16 hydrogen. And we have 4. 16 minus 4. So here is not balanced. To check if there is no mistake, then we have to use the ion electron method to balance it. We have the oxidation number method, which we are using right now. We have the ion electron method and the simple one, which you know. So if we check in details and there is no mistake, therefore it means that we can now use the ion electron method to balance the equation. So I do not have the patience of going all over again. We have more questions here. Assignment to find out what could be wrong in there. We have plenty of stuff here. Let's move on. Okay, quickly. I think we solved something like this. Okay, there is also another method or manner in which questions can be given, which is they have done the first step for you and present it for you to just finalize it. So I think what we want to solve now has been solved, but in a manner which is not the same. So let me bring up that method in case you see something like that, you will not be lost. So we have MnO4 minus plus 5 ion 2 plus give us manganese 2 plus 5 iron plus. So if you look at this question, they have done the calculation of the oxidation number themselves. They have done the cross multiplication, which one takes which themselves. They are just left for us to balance what our oxygen and our hydrogen, and that's all. So they have simplified the work for us. So here we have 4 oxygen, we have 4 moles of water. Now we say I now have MnO4 minus plus 5 iron 2 plus will give me Mn2 plus 5 iron 3 plus 4 moles of water, which is 4 H2O. Now we bring 8 moles of hydrogen, 4 times 2 is 8. So I have MnO4 minus plus 5 iron 2 plus 8 hydrogen ion give us Mn2 plus 5 iron 3 plus 4 moles of water. So let's check the balancing. This is 10 plus 8. No, let's write it down. Minus 1 plus 10 plus 8 give us plus 2 plus 15. So this is 18 minus 1 is 17. 17. I said we've done something like this, but we started from the scratch. This question came halfway up, so it looks not the same, but it's important we see that, so that in case of necessity, we will know what to do. Let's take one more, please. Just one more, so that we can maybe solve one normal question, redox calculation, and see how all of this balancing of redox can be applicable to that. So let's take this. This is 2 MnO4 minus plus 5 C2O4 2 minus give us Mn2 plus 10 CO2. So if you look at this, they've also started. It is halfway up. Let's complete it. They want us to balance our oxygen and hydrogen. So let's see, we have 2 times 4, 8 oxygen here. Whoa. 5 times 4 is 20. 20 plus 8, 28. All right, we still have oxygen here. 10 times 2, 20. So we're balancing 8 because it is 28 and 10 and 20, sorry. So it's 8 that is missing. So we're going to balance 8 moles of what? Oxygen the other way. So I have 2 MnO4 minus plus 5 C2O4 2 minus give us Mn2 plus 10 CO2 plus 8 moles of water. Oxygen is balanced because here is 28. Here was 20. We now have 8. So oxygen is 28 this side, 28 this side. Hydrogen is now 16. I have to add 16 this side. So I have 2 MnO4 minus plus 5 C2O4 2 minus plus 16 hydrogen plus give us Mn2 plus 10 CO2 plus 8 H2O. So, if I'm good, let's check it out. Yeah, I have minus 2, 5 times this, minus 10 plus 16. Here I have 2 only. Whoa. Okay. This is 12. Minus, this is 12 plus this is 4. So something is wrong. I like to check it this time. We have 2 Mn. I think there should be 2 here too. So let me check the question. 2 Mn, yes. Hey, that answer. So if we have 2 here, by cross multiplication, there must be 2 here. Sorry, that was mine. Oh, mistake. So 2 times 2 here will give us 4. That's very correct. And sorry for the error there. So because through cross multiplication, if you have been following what we've been doing earlier on, you understand that the oxidation number here and that we cross multiply them. So if we're having 2 here, 2 must appear here, and where here is 5, there is 10 carbon, which means 5 times 2 here is 10 for carbon. Oxygen there is 20, 5 times 4 is 20. So by virtue of that, it must be equivalent. So I never saw that, I made a mistake. So that's good. So this is it. We're going to stop here in terms of the balancing of redox. But why do we have to be doing all of this balancing that? It is because in our calculation of redox reaction, in terms of, how do you call it, volumetric analysis, we may be required to balance it. When a question comes forward and the equation of reaction is not balanced, we must have to balance it in order to get what we want. So it is on that note that I have to teach us how to balance what? Redox. So let's take a practical question and see how it should be handled to that end. So at least just one. I don't want to take more questions. Let's take just one and see the application of all of them. I'm going to read the question for you. It says 0.02 mole per dm cube of KMnO4 react with 27.52 GDM cube of iron 2 tetraoxosulfate 6X hydrate. And 25 of reducing agent react with 25.6 of the oxidizing agent. If the equation of reaction is given to be this, they've given us the equation of reaction. But presumably, if the equation of reaction wasn't given, what do? You have to balance it. We should calculate the number of moles of water of crystallization. So it is percentage of water of crystallization. So you must, first of all, your brain should go back to the formulas of water of crystallization, which we say the relative molecular mass of the hydrated over the mass count of the hydrated, or the mass count of the hydrated over the relative molecular mass of the hydrated equals to the mass count of the anhydrous over the relative molecular mass of the anhydrous. I give us something. Yeah, now let's say if I have iron 2SO4 dot X water, this is hydrated. If I cut this off, I have H2F2SO4. This is anhydrous. So when I begin to talk about the mass count of hydrated and that of anhydrous, you should understand that of anhydrous does not contain this. It means the water is not in it, it is dried up. So this is it. Let's take the question. Let's start the given so that we can solve it together. Just one, not more than one. So I have my KMnO4 and I have my iron 2SO4.X water. This is for hydrated. Okay. Yeah, we have concentration of oxidizing agent. It's not concentration of acid. This is oxidizing agent, this is the reducing agent. So I'll be talking about concentration of the reducing agent, volume of oxidizing agent, number of moles of oxidizing agent. So let's say, 0.02 mole of KMnO4, which is the oxidizing agent, so 0.02 mole per dm cube. Okay. React with 27.52 GDN cube of this. So this is the, let me write all of this first. Volume of reducing agent, number of moles of reducing agent. This is the GDM cube of hydrated sample is 27.52 GDM cube. This is that of the hydrated. And 25 of the reducing agent, volume of the reducing agent here is 25 cm cube. React with 25.6 of the oxidizing agent. 25.6 cm cube of the oxidizing agent. If the equation of reaction is given, I will write the equation of reaction, then take it out, okay? This is the equation of reaction. MnO4 minus plus 5 iron 2 plus 8 hydrogen give us Mn2 plus 5 iron 3 plus 4 moles of water. I know we have balanced this equation today, but imagine this question is given to you, maybe in exams, and the equation of reaction is not given. We'll give you MnO4 plus Fe2 plus equals to Mn2 plus Fe3 plus. You have to balance the rest. I take out all of this, strip them out, and you are meant to balance it. If you do not know how to balance it, no matter how simple this question is or would be, you can't solve it because the first thing first, you've not been able to balance this. That's why I have to teach you how to balance the equation of reaction first. I have in a series of my videos, balancing of redox reaction, one of my previous videos, which is balancing of redox reaction, you will see this. All right? So you go check it out. So this is it. Let's proceed. I'm going to take this out. Number of moles of acid of the oxidizing agent here is 1. And number of moles of the reducing agent here is 5. So permit me to take this out. Now, the question says we should calculate the number of moles of, let me read it out, sorry. The number of moles of water of crystallization. So this is where we are concerned, the hydrated sample. We have to calculate the number of moles of water of crystallization. For us to do that, the formula says mass count of hydrated over the relative molecular mass of hydrated is equal to the mass count of anhydrous over the relative molecular mass of anhydrous. For us to get the mass count of the anhydrous, we must first of all get the molar concentration of the reducing agent. That is key. If we do not have that, we have to get the molar count. When we get the molar count, then we proceed to get the mass count of anhydrous before we can now apply that formula. So by virtue of that, I have to calculate the concentration of the reducing agent. Here, I have this, so I can use the COA. I can use our major formula to do that. So let me use that. COA VOA over CRA VRA is equal to the number of moles of oxidizing agent over number of moles of reducing agent. So I'm calculating concentration of the reducing agent. That's what I'm looking for. So let's make this the subject. So I have concentration of the reducing agent is equals to the concentration of oxidizing agent times the volume of oxidizing agent times the number of moles of reducing agent over the volume of reducing agent times the number of moles of oxidizing agent. And this is equals to the concentration of the oxidizing agent is 0.02 mole per dm³ times volume of the oxidizing agent is 25.6 cm³ times number of moles of reducing agent is 5. So this is over volume of reducing agent is 25 cm³. 25 cm³ times number of moles of oxidizing agent is 1. So cm³ will cancel cm³, and my answer will be in dm³. So let's check that out and see. 0.02 times 25.6 times 5 equals to this. Divide by 25. This is 0.1024. So this is 0.1024 mole per dm³. Now, normally we leave our answers in 3 significant figures, which is 0.102. But since this is not my endpoint, I'm still moving forward. I just need it in case of necessity. But you should understand it should have been 0.102. All right? Well, let's proceed with that. So I have 0.1024 mole per dm³. Now we've gotten the concentration of the reducing agent. Now we want to get the mass concentration. This is the mass concentration of the hydrated, which is all of this. We want to get the mass con of the anhydrous, which is just this. And what is that formula called? Mass con is equal to the molar con times the relative molecular mass of just this. We're not including it. So if I do that, it is comparatively easy for us to see that mass concentration should and must be lower than this. Because this is hydrated, it contains water. The other one we are calculating is anhydrous, does not contain water, means the value or the mass of water given out should make it be lower. So I want to take this out, please, so that I can calculate the mass concentration of the what? Anhydrous iron 2 tetraoxosulfate 6. So let me take this out. Okay, there we go. Here we go. Mass con of anhydrous. JROUS. Hydrous anhydrous salt is equals to, so let me put it here, GTM cube of anhydrous is molar con of this, which is this, 0.1024 mole per GTM cube times the relative molecular mass of this. The relative molecular mass, let's calculate it first. I'll calculate it, then pick it up and put it there. So I have iron 2SO4. Mass number of iron is 56 plus sulfur is 32 plus oxygen is 16 times 4. This is 64 plus 32 plus 56. So I will be having 56 plus 32 plus 64. And that is 152. So the total here is 152 G mole. So I come here, I write 152 G mole. So that is the mass of anhydrous, does not contain water. So that answer 152 times this. Let me take this out, please. Don't need this. So 0.1024 times 152 gives me 15.5648. 15.5648 G mole. This is, not G mole, this is GDMQ. GDMQ, which is 15.6 GDMQ, approximately to 3 significant figure. But just leave it. I choose to leave this because I'm still moving further. I don't want to take that out. But this is your answer in the real sense of it. Okay, now we have our mass concentration. So let us now apply the formula. What did I say? We should calculate the number of moles of water of crystallization. Let's calculate that. I want to clean this so that I can now calculate that officially. So let me take this out. All of this we must do in order for us to apply or solve that percentage of water of crystallization. We've been able to calculate this, which was not asked. We'll be able to calculate the mass of the anhydrous, which was also not asked, but we should know because it is in the formula. If we do not know, then we are stuck. The formula cannot be applicable. And most importantly, you should also know the formula. If you know the formula, you begin to look for the missing variables and how to get them. That makes it easier too. So let's proceed further right now. Number of moles of water of crystallization X is equals to mass of anhydrous is 15.5648 over relative molecular mass of anhydrous. The relative molecular mass was 152 of the anhydrous. This was 152. equals to mass of hydrated, which is 27.52, over the relative molecular mass of hydrated, which is 152 plus X18. Plus X18. Hydrogen is 1. 1 times 2 is 2 plus 16, 18. So I will be making this X. That's what I'm looking for. Okay. Well, I was looking for X. So we'll call it number of moles of water crystallization, which is X. So this is what I'm looking for right now. I want to calculate to get my X out. So I cross multiply. This times 6 will give me 15.5648 times 152 plus X18, all equals to 152 times 27.52. Okay, let's begin. 15.5648 times 152 is equals to, wow, this is big, equals to 2365.8496 plus this. We have multiplied with this, we have this, we are multiplying this times this now. So 15.5648 times 18 is 280. 280.1664. All of these is equals to 152 times 27.52 will give me 4183. 4183.04. So my X, oh, this times this times this is X here. When we multiply this with 18, give us 280.1664x. So how can I make X a subject? I don't have space, but I want to do that now. It means that 4183 minus 2365 point this divided by this will give me my X. So no space, but now let me do it. Unless I've explained, making X a subject as a science student, as a chemist, or a mathematician, you should know, if I ask you to make X a subject, you take this across the equality sign, it becomes negative, so this minus that divided by this. So I'm going to do that without writing it, so you should take note. So I have 4183.04 minus 2365.8496. Okay, divide by 280.1664, and that gives us 6.5. 6.5, approximately 7. So if the number of moles of water of crystallization is 7, or we have 6.48, which is 6.5 approximately, and if you approximate 4, that becomes 6 point, it becomes 7. So either way, we can still accept that to be 7. So if this is the number of moles of water of crystallization, it means that in this place of X, we replace it with 7, and it will become iron 2 tetrazosulfate 6 heptahydrate. Straight up. Okay, now this is it. Is that all? No, we have not finished. There's somewhere we must go. They say we should calculate. Second question says the percentage of water of crystallization. The percentage. We've calculated the number of moles of water of crystallization, which is X. Now I want to calculate the percentage of water of crystallization. Now, by calculating the percentage, I'm still going to clean the state field that I want to clean it, so that we can do that, and there will be the last part of whatever we're dealing with. So let me take this out now. Yeah. Okay, the number of moles, percentage of water crystallization, which is the percentage of water crystallization is equals to my X water over the whole compound, iron 2SO4.X water times 100. And this is X18, which X is now 7, so 718 over, here is 152 plus 718 times 100. Okay, 7 times 18, 7 times 18 is 126. 126 over 52 plus 126 plus 152. 152 plus 126, sorry. 278. 278 times 100. Therefore, the percentage of water of crystallization becomes 126 divided by 278. 278 times 100 is equals to 45.3. So this is 45.3%. Okay, we're going to stop there for today. It is important you should know that our knowledge of balancing of redox reaction is pertinent, especially in industries. And in this our work, we don't just end in terms of balancing of redox. We're going to use it in calculating what titrometric analysis, which is volumetric analysis. And if we're able to do that efficiently, you begin to see how this is being displayed. And we do not just use it in calculating just water of crystallization. We use it to calculate percentage purity, amount, number of, and many other stuff. Whatever we can do with titrometric analysis, this can be used. So it is very significant that you should know how to balance it, because there may be questions probably in things like exams, maybe a question like this, which you should have known with simplicity, but you do not know how to balance the equation of reaction, becomes a problem. So first thing first, you should know how to balance your what? Equation of reaction, redox reaction, balancing of oxidation number. You should know how to calculate those oxidation number. Check my video, which is balancing of redox reaction. You're going to see how I did a lot of them, a broad spectrum of those kind of questions, and then you can get yourself acquainted with it. So far, we will be stopping here. It was a privilege having you. Remember, these things which we've done, they're essential, they're significant. You don't play with them. I must thank you for your patience, for your understanding, and your the confidence you have probably in whatever I'm going to deliver to you today. For those of you who have not subscribed, don't forget to subscribe and press the notification bell so that you can always get my videos whenever I upload them. It was my pleasure, and it is my pleasure. I'm grateful. I'm happy to be with you today. Do have a wonderful time. God bless you.